Okay, we should get started. So this is the last lecture, regular lecture today. We'll be finishing off some stuff about the short-time Fourier transform and then talking about some issues in interfacing to continuous time. And then next Monday is the last day of classes. We'll have our lecture, but it'll be the project presentation. So we have seven groups that have volunteered to give talks about their projects. I sent out email yesterday to those people with some advice on how to present. So hopefully everybody knows that they're presenting, and everybody who thinks they're presenting got that email. We'll look at the list at the very end. And then, let's see. So that's Monday, project presentations. And then the week after that, Monday the 16th, will be the final exam, which I believe is in here from 9 o'clock in the morning. We might have to we might have to have a little bit of spread, but that's the show up here. I'm thinking about having a review session a week today, next Wednesday. Is that of interest to people? Okay, so we'll meet again next week, but it'll just be, I'll be here, and you can come if you want, and I'll just be, reviewing the stuff that we've done for the second half of the semester and answer any questions. Yeah.
Can you still hold office hours next Thursday as well?
Will I hold office hours next Thursday?
Yeah.
That's a good question. I wouldn't, I would normally plan to, but I just let me see if I've got anything on my calendar. So yeah, I'll be in my office next Thursday. I won't be in my office tomorrow. I have a thesis defense down at NYU tomorrow, so I won't be around. I'm sorry about that, but this thing was scheduled months ago, so I can't avoid it. If you have questions, if you want to meet, then send me email, and we'll try and set something up. But I will be around a week tomorrow. Okay. Any other questions? I should put that on my calendar and make sure I remember. Okay. All right. All right. So we just sort of gone through this whole discussion of the short-time Fourier transform, of how basically, very simple idea, rather than taking a Fourier transform of an entire signal, we chop it up in little pieces, which is the same as taking the entire signal and multiplying it by a little tapered window of short duration, which just filters out, sort of selects out the time in some particular range. Then we take the Fourier transform of that, and because it's a short length of non-zero values, we can just take the DFT over that point. We get a little column of spectral values which we can put on a picture at that particular time, and then if we stack up all those columns, we get this image, which with the one axis is time, the other axis is frequency. This is the DFT axis, and then we can set the color or the intensity to show the actual amount of energy. And the spectrogram, as it's normally drawn, is using a dB range, because this logarithmic range is more in line with our perception of what signals are important, or in other that's specific to hearing. But in other applications, we often care about signals over a very wide dynamic range. So it's usually useful to plot this in a log axis so we can see, even low-level detail. And it's not a tremendously good representation of what's perceptually available in sound, for instance. But it is quite straightforward. It's easy to predict it's easy to understand what it's saying. And so this is actually a very, very useful tool in sound processing for sure, and doesn't really have any rivals in terms of what people use. People have some special purpose visualizations, but this is the most popular one. And yeah, that includes plotting it this way up. MATLAB has said that specgram is deprecated and it's going to be replaced by a new command, spectrogram, or something like that. And spectrogram sort of does the same thing, has slightly different arguments, but it plots, to my mind, upside down. It has 0 frequency going down to higher frequency. And that's so annoying because for decades people have been plotting spectrograms this way up. This is the way you always plot them. If I see them upside down, it's just really hard for me to look at them. So please plot them this way up. And then, the MATLAB will auto-scale, and typically if there's any regions of pure zeros, the auto-scale will go to negative, very large number. So you normally want to manually control the color axis, the depth axis, so that you only get 60 or 80 dB of range, because more than that, if you have a 300 dB range, then the interesting part, which is the top 50 dB or something, gets compressed, and so you can't see any detail. So it's good to set that explicitly, and it's good to use the color bar command, which just makes this thing appear, so that whenever you have a plot like this, whenever you make a plot, it's just good practice to label the axes. Spectrogram automatically labels the time and the frequency axes for you, but if in a plot like this, you've basically got 3 axes, you need to label the vertical axis as well, and that's what the color bar gives you. Yeah?
Let's consider the audio signal.
Yeah.
It's just a single tone, simple one sine wave or a
Yeah.
constant. So in that case, will the spectrogram be uniform throughout?
Yeah.
Exactly the same color everywhere?
Oh, no. So that's an interesting question. So what happens if we have a sine tone? So we had one of these last week, right? Or was it C on Monday? Cosine. No. Come on. Here we go. So so here is our sine tone. Let's get rid of that. Plot that. Okay, sine tone doesn't look very good at this level of zoom, but if we zoom in, it's just a tone like this. Okay, and if we listen to it, so SR is, okay, sound SC, C1 SR, sine tone. Okay, so what is the specgram of this going to look like? Specgram using the the second argument is the FFT window length, and then the third argument is the actual sampling rate. And this is what it looks like. So it was a 1,000 hertz tone that we generated, and so this is the color map is actually kind of a little hard to see here because the color map the default color map actually gets, oops, was it? Color bar. The color map they use has the sort of brightest part in here, and it gets dark at the top. So it goes very rapidly into this very dark part. I actually I often prefer a grayscale color map, which is color map. I actually like 1 minus gray. You'll see what that does. So now it's white where there's no energy, and it's darkest, it's black where there's the most energy. And here you can see the sine tone just has this narrow ridge right at that particular frequency, which is what you expect. And if we had what was that, C? If we had a signal which was zeros, right, for 16,000. But then, what's so notice it auto-scaled here. So we've got this range of 130, 140 dB, which is what I just said not to do. So you'd normally take this one and C-axis it. Well, it wants to get up to 30 dB, so I would typically do from minus I give it a 50 dB range, 80 dB range, so minus 50 to 30. And so now you see that these flanks, which are really just the sort of the spreading of the analysis function, those are basically the side lobes from the Hanning window they're using. They disappear very quickly, so it's really just the energy there. If we had a signal that was all zeros, but then I put in a delta in the middle, so S8000 equals 1, like that. Oops. 1. What? Oh, yeah. I guess I have to give it one dimension in the other axis. And then this had clicks at the beginning and end from turning the audio on and off, and then it had a click in the middle, which is actually the click. If we look at the spectrogram of this, then it's like it's even color bar. Now it really is doing the minus 300 dB thing, but it doesn't matter because there's literally no energy anywhere except in this one middle window where there was a delta, and so the Fourier transform of the delta has uniform magnitude for all frequencies, and so we see this thing in here. So that's
Time scale, that's 0.5.
Yeah.
That corresponds to the time instant when we gave the impulse.
Right. So the sound was 16,000 samples long. Somehow the sampling rate is 1 second, right? That's right. So sampling rate is 16,000. So it's 1 second's worth of sound, which is what we see. Right. The time axis is 0 to 1. But then I put in the impulse at 8,000, which is like halfway through. So that's time equals 0.5 seconds. Of course, if I put it in at 8,100, it still would have fallen into that same window. It would have looked the same, but something like that. I think maybe there's a... Yeah, no, it's that just it falls exactly. If I put it in at 8,100, it would have probably hit 2 windows. Here it just hit just the one central window. But if I offset it slightly, no. Oh, okay. There are actually two. There are two. It was symmetric around 2 of them. Okay, hang on. Let me just show you what I'm trying to show you. 8200 spectrum, G color, C-axis. C-axis tells you what the range it's using. It's using minus 300 to 0. So I want it to be instead minus 80 to 0. Okay, now you can see, I don't know if you can see, but there's actually 2 bins in the middle here. There are 2, because the spectrum by default uses 50% overlap, so it'll use one window, and then it'll use the half of that one and half of a new one. So the single point falls into 2 windows, but now it's sort of in the middle of one of the windows and slightly off to the side of the next window. So there are 2 windows here with impulses in them, but at different amplitudes because they fall in different parts of the Hanning window, so they have slightly different colors of gray. That's just this is, as it were, the time blurring that the 50% overlap has given us, making that impulse appear slightly blurred out in time. Okay. Like I said, spectrogram, this is I use this a lot. It's a very powerful tool, very useful tool. We came to the spectrogram by thinking about it as a succession of columns, right? Each column is a short time is a DFT of a little short time section of the original signal. But you can also now think about it as rows. That if I look at this 2,000 hertz row, then I see this. This is like I can think of this as a slice, as a vector of values, showing how the energy varies in that 2,000 hertz band with time. So if we think about this now, we had x of k and n0, but let's just think of x of k as a function in its own right, a function of n0. This is for some bin of the spectrogram. But we can, if we write down what the short time Fourier transform was, right, it's just this window time signal times the DFT constant, DFT function. We can rearrange this as a convolution, right? So we can change the variable here so that we've got n0 minus m as an argument to x, and then combine these two and change the variable into some impulse response, h sub k, where this impulse response is just the time-reversed window function and actually the time-reversed conjugate complex sinusoid, which becomes just a positive going complex sinusoid. So this is slightly strange because now we've got an impulse response which is complex, right, which we don't normally see. But okay, fine, you know, it's just numbers. We know how to take, we can convolve with this just fine. That's what we're doing. So that means that we could get the spectrogram by building a set of filters with this impulse response, with these impulse responses, one for each k, one for each bin of the spectrogram, and just running our original signal through those filters and then taking the output of those filters and taking those as the values of our STFT. Normally, we don't calculate the STFT for every value of n, right? We only calculate it for some, you know, hopped value, like half the window length, something like that. But we could do that. We could just run the filter, and then we just only keep every big N on 2 sample, something like that. But if we did do that, the actual value we get at particular times would be the value that we get by calculating DFT. It's a little bit like, you know, when we calculated when we used the Goetzel algorithm to calculate the output of a DFT at a particular point by running a filter. Same idea. So if this is our filter impulse response, and because the window function is normally symmetric in time, you know, the fact that we had to time reverse it doesn't really make any difference. So we've got some impulse response like this, then we can say, well, what's the frequency response to that filter? What is the range of frequencies that it's selecting? And that's kind of easy because it's just, well, in time domain, it's just the product of two things, and one of the things is a pure exponential sinusoid. So the frequency response is just the Fourier transform of the window shifted by this sinusoid, modulated by the sinusoid. And then, of course, we've got k or n of these things, one for every DFT bin k. So we end up with a set of, here's like the Fourier transform of the window function, which may be, you know, maybe it's a rectangular or a Hanning or something, so it's got main lobe and some side lobes. And then here it is for some particular value of k, which just means it's been shifted by k 2 pi on n, by 1/nth of the full band here. And so if we look at all k of those filters on the same plot, we get something like this, where each filter has a different bandpass response. The bandpass response is dictated by the shape of the window, which is sort of intrinsically low pass, and they're all overlapped like this. And so you typically get something like this, where they overlap a little bit, depending on how long that window is, but you sort of get this uniform coverage. And so this kind of structure, where you have a set of bandpass filters that are kind of covering the entire frequency range, is called a filter bank. And so the FFT is like looking at the output of a filter bank, a set of filters, bandpass filters, tuned to this bunch of frequencies. I mean, it's kind of, in fact, the spectrogram predates signal processing. No, I don't know if it certainly predates digital signal processing. And in the original formulations, people were interested in how can we visualize sound. They actually would build a set of resonators, right? So maybe mechanical bandpass filters, and then have some way of having those resonators modulate some image. It was actually, done with, I forget, I don't know the exact details, but it was like depositing soot onto a piece of paper that was sliding by. So they'd have these resonators, but it was the same thing. Basically, those resonators are simple bandpass filters, and then you take the magnitude of the energy coming out of each bandpass filter, render that onto a page somehow, and you get an image like this. And so, although now we're doing it with the DFT or the FFT, it's intrinsically what you're doing is just looking at the energy in each frequency band. Yeah.
So we're actually modeling each of those STF, each of those Fourier transform bins.
Yeah.
As bandpass filter.
Yes, exactly.
So I mean, like, how can a FFT act as a filter? I mean, if it itself filtered out some components, we can't actually take them in the first place. Right? I mean, it's supposed to show those components as well.
So that's interesting. How can an FFT be acting as a filter? It's the combination of time windowing and then taking the Fourier transform, right? So if we just took the Fourier transform, then we just get the energy at a particular frequency bin across all time. But now we've windowed it in time, so now it's like, well, it's only at this particular point in time that we're looking at it. And then we take the frequency components. But if we sort of looked at it the other way around, as say taking the frequency components and looking at them in different points in time, that feels more like what a filter does. So if it was infinite duration, then taking the Fourier transform would give you the energy at an infinitely narrow frequency range, right? Just a single frequency. By limiting it in time, by applying this time window, we've compromised the frequency resolution. We've ended up with a Fourier transform that's going to be spread out in frequency. And so now it's like, oh, it's not a single frequency. It's actually a band of frequencies. And so the output of that Fourier transform that's been limited in time is the same as the output of a filter that has some finite range of frequencies at a particular point in time. That's how to think about it. Mathematically, you can see what's going on here, right? That this has got to work. That the STFT, we can rewrite it as the convolution of, the signal and some impulse response at some particular point in time, and so then that means that the output is just the output of a filter. But how did that happen? How did the Fourier transform become some broader range of things? And that's kind of the explanation.
So let's say, so when we give a band of frequencies to an STFT, then that basically has some weight for each frequency. So it doesn't detect every frequency equally. And suppose we want to use.
Yeah. So here now it's like, okay, wait. You're telling me this is a bandpass filter, so each bin of the STFT is describing the energy in a range of frequencies. Then you're asking me to use it to figure out where the energy is in this signal with more frequencies. And so basically, this is this is about resolution. That what is the finest frequency that you can discern with your spectrogram, with your STFT, and that is finite, right? So if we look at them, we haven't got a good one up right now, right? But if we go back to the, some real signal here, then we've got a sort of a continuous frequency axis here, but we've actually got individual pixels in here, which are the individual bins of our, it's very clear that there are pixels here. They're the individual bins of our DFT and then our time windows. And so, yeah, if there's a frequency in here, we can't really tell where it is in here. And that's because they're falling into the same bin of that effective bandpass filter that row of the STFT corresponds to.
So if we reduce the length of each STFT,
yeah,
then probably the scope of our frequency for the bandpass filter, all the images getting narrower would be higher, so that we can detect more resolution.
We have to make the time window longer to get our frequency response to be narrower, right? Because when we make it longer, here's one way to think about it, right? I've got this chunk of signal, it's 16,000 samples long. I can use 256-point samples, every 128 points something. And then I end up with a 256-point FFT, which I throw away the top half. So I end up with 128 frequency bins. Now, that's like, well, which means that each one is only 128th of the Nyquist frequency. I really want to get fine in that. So now I'm going to have to get a longer FFT. If I take a 1,000-point FFT, now when I do the Fourier transform, I get 1,000 points. I get 500 points up to my Nyquist range. Now, the windows I have to take in time are 1,000 points. They're 8 times as long as they were before. So they're sort of more blurred out in time, but I get the extra frequency resolution back. Great. Okay, so STFE is a filter bank. One interesting way of thinking, if we have a bunch of bandpass signals with overlap between all their frequency ranges, then maybe we could just reconstruct the whole signal just by adding together all these bandpass signals. We've got frequency, we've got coverage for all frequencies here. When you do that, you have to be careful in general because there's going to be overlap here, and if the phases don't line up in this region of overlap, then you're going to get weird stuff going on. But in general, it's like, oh, maybe we can reconstruct. And so, yeah, you can do that. And of course, we could do that already if we think about, well, all we did was we windowed out a chunk of signal, we took its FFT, its DFT. If we just took the inverse DFT of each of those individual slices, then we would get back the individual pieces of time window, and we could just add those or stick them together, and we'd be all right. So if we have a time frequency representation STFT like this, which is just the DFT of each of these, then we take the inverse DFT of each of our frames. Notice here we have to have the full complex DFT. The spectrogram only tells us the magnitude. We need to know the phase as well, but assuming we kept that, we recorded it somewhere, then we can take our IDFT, we can recover our windowed chunk of X. We have to make sure we get our times exactly, properly aligned so that we understand that we need to shift this little piece of signal by n0 to figure out where it was in the original. But then we can just put them down, take each one and put it down on a time axis, and we reconstruct our original signal. If we did it like this, if we had no overlap between successive windows and we had a tapered window, then we'd end up with the signal multiplied by this window. If we knew what that window was, we could divide through by Wn, divide through by this envelope and recover the original signal. That would be okay as long as Wn didn't go to 0. Here, mostly it's not 0, but it gets quite small at the edges, so that's not ideal. You don't like to divide by small numbers. But anyway, to get our nice-looking spectrogram, we probably wanted to overlap these windows anyway. And so then when you start laying them down in reconstruction, you get these overlaps. You can just sum up in the overlaps. If you have a window, well, you end up with the sum of these windowed things. And then if you've got an overlap, you're going to get x of n times the sum over all these overlap windows of n minus RH, where h is your hop size. And then if you choose your window and choose your hop size such that this thing is constant or this thing is 1, then just doing the inverse transform and overlap, adding the results, adding up the results at the appropriate overlaps will give you the original signal back. And so it turns out that with a raised cosine window, of course, if you've got two cosines like this, and they overlap at the 0 crossing here, so that's symmetric, then when you sum them up, they're exactly complementary, so they sum up to a constant. So that works for a Han window, it's 50% overlap. For a Hamming window, which was the cosine with a little bit of a DC offset, it also works, just you get a slightly larger value as your constant envelope. But you get you can just sum up these reconstructed values and get a full smooth time domain. If you mess this up, you end up with this sort of modulation of the reconstructed signal at the frame rate. You get this frame noise coming in, which is normally you may come across at some point. You'll recognize the sound of it when you hear it, or you'll figure out that's what it is. But if you get it right, then that disappears, and you get this nice signal, reconstructed signal. And so now we can take a short time Fourier transform. Now we've got our signal described as in terms of its energy at every time, every frequency. We can mess with that. We can change, say, the magnitudes of the energy at different times at different frequencies. And then we can just put it back through this reconstruction technique. It's a little bit, it's a little bit rough and ready. It's a little bit quick and dirty. But you get something back, and you can actually use that as a way of modifying signals. And that's a pretty powerful medium for changing signals. So here's a very quick example of this. We take some speech, and here it is as a spectrogram, as the short time Fourier transform magnitude. we can have the same signal but with noise added. So here, this is the spectrogram of this speech, but with some white noise added, so you can see that there's all this energy in the background. Where the speech is very intense, it sort of dominates, but everywhere else you get this noise. And then, a very simple noise reduction strategy would just be to say, well, the noise seems to be mostly up to this sort of greenish, yellowish color. So if I take all cells that are that big and then squash them to 0, then I'm going to remove all these noise cells. I'm going to remove a bunch of the speech as well, but I'll still keep some signal here, which will just be the speech signal. And so I could get a signal which looks like this. Right here, this is exactly what I did. I just took the STFT, set a bunch of the bins to 0, resynthesized using overlap add, and then reanalyzed. Actually, I don't know if I really did that. But here, it's in this week's MATLAB script. Or it would be if the network was working. But here's what it actually does. We have our initial signal. I hope. I don't know why this thing sounds so bad, but anyway. I can add noise to that. So I can just take D and then add some random noise like this. It's not helping at all, huh? There's some loose connection in here. I thought I fixed it, but oh, here we go. No, come on.
Football team coach.
Okay. And moving on, I can actually use specgram. I can use specgram to calculate short-time Fourier transform, but MATLAB doesn't provide a function for inverting that. So I actually just for simplicity, I wrote my own functions to do short-time Fourier transform and inverse short-time Fourier transform. And so they just take the signal, the window length, the FFT length, the window length, and the hop, the advance between successive windows. So that, and then if I just do image SC of 20 times log 10 of abs of D. So I take the magnitude, take its dB, and then plot that as an image. I get this, which is upside down, and then I do axis XY, then it turns the right way up. So it's the same image, but just as the actual values of a matrix. And if I do this now for the noisy signal instead, I know why I have to transpose it, but there it is. And axis XY. So that's kind of the picture we saw on the slide. I haven't fixed the color axis like I should have done, but basically here's all the noisy parts. Here is all the speech parts. And so if we look at if we do a color bar on this, then sort of we're saying that, well, down to around these orangey dots are about minus 10 dB or something. So maybe if I remove everything below that, I can get a reasonable mask. So I can have, I'm saying minus 15, I can set a binary mask here by saying, well, for every one of these log values, if it's greater than minus 15 dB, I'll keep it. Otherwise, I'll set it to 0. So now if I look at the C of M, axis XY, this is, make that black and white. So this is the mask, C-axis minus minus 6020. And line them up, put in color bar on both of them. Okay. Here is, that doesn't look right actually. What happened there? Why is this on strange? Okay, here we go. Here's the noisy spectrogram, and then here's the mask of all the time frequency cells that have a level above minus 15 dB, above around here. And you can see there are a few around in the noise, just because noise has this kind of, distribution. So sometimes it has large values, but mostly it's concentrated around these points where the speech pokes through. And so what I'm saying is I can now use my ISTFT routine let's say the reconstruct, here we go. No. The reconstruction is going to be the ISTFT, the inverse STFT. If I just do it for E and then keep everything else the same, I get the original signal back. Oops.
Football team coach at the watch, Dennis Zidane.
But if I do M, if I scale each point in E by my mask like that, here's what I get.
Football team coach at the watch, Dennis Zidane.
I'm sorry about the thing, but you can hear that basically it's speech without the noise, but with this funny glistening or glinting sound. If we look at the spectrogram of this now, oh, that's nice. It's kind of clear what happened here, that here are the different pieces of the speech that were kept by the mask. But here are those individual little spots that we saw in the time frequency mask, the black and white mask, where it was a single cell in this spectrogram that had an energy high enough to make me think that it was maybe, it got through the mask. And then when we reconstruct it, basically we get this one bin in one short time Fourier transform window, which is turned on, which is like a little sinusoidal pulse. And so it gives us that little tonal burst that's usually referred to as musical noise. It's a very widespread problem in this kind of noise reduction. And then that's what it looks like. So that you get something where most of the noise energy is gone, most of what's left is the speech energy, but we do get this kind of annoying noise in the background. Yeah?
Is there a delay for it, or it's just scaling? Since the signal's kind of shifted?
It's just shifted because of the color bar. There shouldn't be any delay. So if I put color bars in all of them, they all line up. Does that make it clearer? Yeah, it should be like every individual frame, if the ISTFT routine is doing its job properly, then every individual frame gets converted back into a chunk of signal which lines up in the same place. Yeah.
So in a case where most of the noise is concentrated in the audio range and not in the high frequency range,
Yeah.
then it gets more and more difficult to reduce this noise by this method. Because whatever we are chopping up the noise is basically for all the values greater than whatever is the audio frequency for in high frequency range, basically.
Yeah.
So if we get the inverse transform of that, we still have the noise bins or noise tones which are present in the audio range, because we don't want to cut down on the audio signal
Yeah.
in the first place. So so this reduces noise to considerable extent when the noise is concentrated in high frequency ranges. But if the noise is concentrated more in the audio range,
Yeah.
then
Right. So here, all we're doing to remove noise, we're removing entire. So this is, if we had a signal and some noise, this would be the classic case that we've been sort of implicitly thinking about when we're doing filter design. We just design a filter that passes the signal band and removes the noise band. It would just be a fixed time invariant filter, and we'd be done. What's happening here is it's actually equivalent to having a single filter for each of these slices, each of these spectral slices at particular times, within that one little window, it's a time invariant filter, but we're changing the filter for every successive time slice by choosing a different, basically, it's the filter to find the frequency domain, but it's the mask, is the, applying to the DFT. And so we're changing that, but it's a locally constant time varying filter. But we've still got the same problem that, well, if we've got frequency regions where we want to remove the noise, we set them to 0, and if we've got frequency regions where we've got signal, we let them through. If we have a situation where the noise is in the same frequency range as our signal, then this kind of linear filtering is not going to help us separate those. It's like you can either keep this frequency band or remove it or attenuate it, but if there are frequencies that come from the signal and frequencies that come from the noise, and they're added together, then linear filtering is not going to be able to remove them. So if the noise is down here in the same frequency bands as the speech that we kept, then we don't remove that noise. The amazing thing is that for perceptual problems, that often doesn't matter. That typically the speech, because the speech varies so enormously in its energy in different frequency bands, that suddenly it's going from some small value to 40 or 50 dB larger. As long as the speech is like 10 or 20 dB louder than the noise that's added, you can't detect it. That's the basis of psychoacoustic coding, of MP3 coding. It doesn't give you a particularly good signal-noise ratio, but it manages to keep it above 15 dB, but within a very narrow frequency range, and you can't hear the noise if the signal is 15 dB above it, as long as it's the same frequency band. So that's not a huge problem. That if your signal is also present where your noise is, as long as your signal is louder than your noise, at least locally, then it's okay to keep everything. It's just a question of making sure that in situations in bands where the noise was louder than the signal, you remove those altogether, because that's going to sound like noise if you hear it. Of course, if you've got a signal where the noise is louder than the signal everywhere, you're in big trouble. There's not much you can do to recover it. You lost a lot of information. Yeah?
I have a question about the fact that, let's say, arbitrary constraint that we put on the variation of energy along the frequency axis
Yeah.
at local time points. We said that we need to constrain the energy to be 0 if it is below some certain threshold. Let's say we do have an example with more gradual variation along the frequency axis, not that arbitrary pattern.
Yeah.
And we set that threshold. So it's like applying at a local time ideal low-pass filter.
Yeah.
But this is perfectly constrained on the frequency domain.
Yeah.
So it's blown up in the time domain.
Oh, so okay. So that's a nice point. So these filters that I applied, right? I already said, okay, well, we've got this time frequency mask, which has set certain values to 0, and we could think about it just one column at a time, and then it's like, okay, it's a filter applied in the DFT domain, setting some bins to 1 and some bins to 0. So if we plot its frequency response, it's this nice ideal thing. It could have been like, we set all the bins below. We set all the bins below some frequency to 1, and then all the bins above some frequency to 0. Right, so this is omega, or actually it's k for our DFT, and this is the magnitude of some filter that we're applying. So wait, what happened? We just had an ideal brick wall filter. Well, actually, it wasn't a continuous thing. It was a DFT, so all we did was we had a set of frequency values which were spread out, and we have something which looks like this. What we end up applying, but also what we know is, well, this thing actually only applied to a single, window chunk of signal in time. So when we apply this in the frequency domain, so we had, R of, and then this is an STFT, right? So it's R of k and some time index was equal to our mask, h of k and m, times x the actual signal, x of k and m. This was in the DFT domain, which means that for some, this was maybe some window, some window piece. But so in the time domain, it should be there was some x window of n, which was convolved with some h m of n, which corresponded to that, and that gave us some little piece of r, right? Some which we can overlap. The notation's getting kind of sloppy here, but the point is this multiplication corresponds to convolution with something. What is this thing? Well, it's just the inverse DFT of this, but if I have... there are a couple of things that go wrong. One is like, well, that's got a limited frequency resolution, that is actually, it's not... we're going to have some kind of... I want to say Gibbs phenomena, but Gibbs is in the frequency domain, right? So what happens when we put it back in the time domain? We can't have this thing extend out infinitely because it's only a finite length signal that we're dealing with. So we have some kind of some edge effects that spill over. But basically, we're limiting them what they can look like by this time window as well. So the interesting question then is, well, okay, so if I really want, what is the actual filter? I know what the values were on these samples because I constrained them to be ones and zeros. What was the actual filter I applied? The actual filter I applied can be something like this, right? It has to go through these points, but it doesn't have to be nicely behaved in between. So even though we think we've applied an ideal filter, it actually is not ideal. It's just that it's just happened to line up on the points that we wanted the FFT, that we took the DFT on. And that by having this sort of more spread outness in frequency, that's why it can end up being it remains local in time. The effects have to be within that one short time Fourier transform window. This is more subtle than this, right? You can see, like, well, okay, I get an idea now. There's a couple of things which are not quite what we think. But the actual detailed, if you try and figure out exactly what happens is, you know, we're reconstructing an individual window like this, but when we arbitrarily modify it in time, what we were doing was we were assuming that we'd done some nice tapering window on the analysis time. Then we modified in the frequency domain. We actually end up with something which is not shaped like this at all. Now it's got some weird, nasty shape when we do the reconstruction because we just, you know, the nice shape was to do with the exact cancellation of adjacent sinusoids. So when we do this arbitrary modification, typically we then have to make it work, apply the tapered window again before we do the overlap add to get rid of nasty edge effects from here. And then we have to have like 25% overlap because when we've applied this window twice, we get a cosine squared function, which now we have to overlap them more densely to make it work. And then it sort of works. But the actual filter that you end up implementing is, you know, not that obvious. It's not necessarily the filter that you think you started with, because there's some time aliasing that goes on. Yeah?
But if that works, what's the point of using a denoising filter on the time domain? If we can arbitrarily set some things to be zero in the frequency domain,
Yeah.
what's the point of convolving the time domain or using all those fancy techniques? If it works theoretically, what's the point of doing anything else?
Probably the answer is it's going to be there's going to be some equivalent thing, right? So you can if you can do it in the frequency domain, you can do it in the time domain. So it's like, in some sense, it's just a question of implementation.
What I'm saying
Right.
is that it cannot be so easy. That's why.
Well, the interesting thing is you end up with different things. The actual what you get in the frequency domain is actually a little bit difficult to express exactly what you get in the time domain. And there are some things which are not ideal, right? There are all these effects of what happened when you actually applied the window. You did some spreading, right? So the spectrum you're modifying in the frequency domain is already the time domain signal after it's been blurred out by this short time window. Okay, so it's not exactly what you thought. And then there's this whole thing of exactly what you get back when you reconstruct. Because now what happens is we're going to take another window here. We're going to do the reconstruction again. We're going to overlap add that. The actual signal we get at the end is the sum of these two things, which are, because they've been modified differently, they're not going to line up exactly in the overlap region. So you're going to get some interesting overlap effect, and so it's a little bit hard to say exactly what you're going to get in the time domain. And so it may be that maybe this doesn't, maybe this doesn't give you what you want at all. It turns out in practice it does work pretty well. That, like we just heard, it gave us something which was pretty similar to what we expected, which maybe we just got lucky. So sometimes working in the time domain, you can be much more precise about what you're trying to achieve. Or working in the pure frequency domain, you can be precise about what you're trying to achieve. In this short time Fourier transform with overlap add, there's quite a lot of caveats about what you're getting. Maybe that's the best answer. But I mean, I introduce it. So this is yeah. As we've just seen, there are quite a lot of there's quite a lot of hand waving going on about exactly how this corresponds to what we're getting compared to the straight up Fourier transform that we've seen before. But this does work in practice, and it's pretty popular in practice. So it's worth mentioning and introducing here. And it works. You don't have to. Normally, if you don't worry too much about these details, it still kind of works. Although clearly, if you when push comes to shove, you have to look in more detail at how these things play out. Okay. It's probably as much detail as we need to go into now. Something that would be covered in more rigor in a higher level class. Okay, let me spend a few minutes talking about this continuous time stuff. Basically, the main thing I want to say is just to sort of go back over this idea of how we relate the spectrum in the continuous time with the spectrum in discrete time. I've already said basically that, well, they're the same, at least up until the Nyquist frequency, and they're just proportional, right? That the discrete time frequency is just t times the continuous time frequency, where t is the sampling interval. So there's this constant proportionality. That's how we do the translation of specifications in Hertz into our discrete time system. But there's kind of a nice second way of looking at this, which I just want to go through. So here's the scenario. We've got the real world. It's intrinsically analog and continuous time. We've got our DSP, which is operating on these sampled sequences, and we connect them together by an A to D converter to get the input, and then D to A converter to take our sampled sequence of an output and generate an actual real-world signal. The A to D converter has something which just takes analog voltages and turns them into digital numbers, but it also has the sample and hold, because typically the thing that builds a digital number needs to look at the voltage for a little bit of time to figure out each of the individual bits. So we have something which will look at a voltage at a particular moment and then hold it constant by storing in a capacitor, for instance. And then we're also going to need this anti-aliasing filter, which is this thing that basically removes the things that would be the components in the signal that would be moving too fast, so that when we sampled them by closing the switch, we'd get variation that we couldn't account for. So we have this kind of low-pass filter to remove aliasing. And then we have the D to A converter can similarly generate voltages at every individual instance with like sharp transitions between. And we have a reconstruction filter which will smooth them out, basically removing the same high frequencies to give us our thing. But how do we, how do we understand where these low-pass filters are coming from? So let's just go quickly. Let's try and go through this sequence, this argument. We can think of we know that the discrete time sequence is defined as being some continuous time signal sampled at multiples of a sampling period t. So n is our index in our discrete sequence, and so we're saying that's equal to this value of this continuous time, continuously valued signal at some particular instant, n times big T. And that gives us our sampling frequency as inversely proportional 2 pi over t radians per second is the sampling frequency in radians per second. So we can think about this signal as having a continuous time Fourier transform defined like this. And then we know that this signal has a discrete time Fourier transform defined like this. So this is just the DTFT standard expression, the CTFT standard expression. We know that G can't in general hold all the information in G sub A because the analog spectrum may have higher frequencies than we can distinctly represent in discrete time. So if we do this, it must be that G is completely defined by G sub A. So what is the relationship between them? So one way of thinking about this is to think about this intermediate signal, G sub P. G sub P is a continuous time signal. It's a function of our continuous time index. But it basically looks like the output of stem function. It looks like our discrete time signal. And that's because we generated it by taking our nice, smooth, continuous function and then multiplying it by an impulse train. This is a continuous time impulse train. It's a sum of these continuous time Dirac functions. But it just means it's a signal which is 0 for most values of t, and then takes on a non-zero value for an infinitesimally small range of values of t around each multiple of big T, such that when you integrate across them, you get 1. So this GP of t is really, it's exactly the same as our sampled sequence, but rather than being a sequence of discrete values, it's this weird continuous time function that only has non-zero values at these very short instants. But it's kind of, it's still got the same information that we have in our discrete sequence. So what is the Fourier transform of this sampled G sub P of t? So G sub P of t is GA of t times delta of n minus t minus nt. If we think of it as the sum of these things, right, it's G of A times the sum of these deltas. At each point, the actual value of G of A is just the time value. It's G of A at the particular time value where this delta is non-zero. So we can take this little t and replace it by big NT in here. So now this just becomes a set of a sum over weighted deltas. Like we also spoke about that in terms of the discrete time domain. And so then we can think about the Fourier transform of this as just being by linearity, the sum of a set of weighted Fourier transforms of deltas. The individual deltas in continuous time now these are just like, again, linear phase things. So they're just these linear terms here in the spectral domain, right? The Fourier transform of a delta is a complex sinusoid whose linear phase, whose frequency, as it were, phase variation as a function of frequency is just some constant. So we end up with this expression for G sub P as a function of big omega here, which looks exactly like our expression for the DTFT. G of the function of little omega is the values, right? So GA of NT is exactly just G of N. That's the definition. And then E to the J omega little nt looks like the same as J little omega n if we set little omega to big omega times t. And so this is basically just notation. That this is what I think I said before, there's really only one Fourier domain. All this work we've done talking about the little omega, the discrete time domain, it's really just mathematical window dressing on something like this. That we could have done it all, staying in continuous time, dealing with these impulse train signals. The math would have been exactly the same. It's just that we would have been dragging around omega, big omega t rather than little omega. So mathematically, they're the same thing. But if we want to think about it, then we can think of them as like two different domains, but they happen to have the same value. So here's our plot of big G sub P of J big omega, which is the continuous time Fourier transform of a continuous time signal that happens to have a lot of impulses in it. And then here is our G of e to j omega, our discrete time spectrum that we're thinking about. And it's the same function. It's just that we label the time axes different. Here we label this as omega, here we label as little omega, and then this pi point here becomes omega sampon 2 in here, right? And the 2 pi point becomes omega sam. So this was this plot of these two things lined up that we saw before. Once we think about it like that, then we can say, okay, well, that's G sub P of big omega. how does this correspond to G sub A, the actual original analog signal? Well, G sub P of t was G sub A times P of t. P of t was our impulse train like this. P of t is periodic with period big T. A periodic signal in continuous time has a Fourier series representation, so we can express P of t as the sum of a set of harmonics, complex sinusoids at multiples of 2 pi on big T. And by using our Fourier series expression, the individual coefficients, the CKs, are just these integrals of one cycle of the signal times the conjugate harmonic. And so this, because this is a delta function over this period, it just comes out to be 1 over t. So basically, it's the uniform, the P of t is a set of deltas in time. It's also a set of deltas in frequency. It's the harmonic series of equal amplitude, all multiples of 2 pi on t. If we multiply something by a complex sinusoid and then take its Fourier transform, then of course that's just shift in frequency. So it's still for continuous time, but it works the same in continuous time. That we're just modulating it by omega 0, so the whole Fourier transform just shifts by omega 0. So if our GP was G of A multiplied by this, then we can, by linearity, the spectrum is just going to be the original spectrum G of A shifted by all of the individual harmonics here summed up. I went through this fast because we're running short of time, but that's the key idea, that by thinking about this impulse train as the sum of a set of harmonics, set of sinusoids, then when we multiply by that sum of sinusoids, we can think about multiplying by each one of those sinusoids individually and then summing it up. Multiplying by any one of those sinusoids just gives us a shifted version of the spectrum. And so the overall spectrum of what we get for this gated continuous time function is a sum of shifted versions of the original spectrum. So here's the picture. This is the original time domain function, a smooth function in time, which has this spectrum here, G sub A of j omega. This is the original spectrum. And I've drawn this one to have a band-limited spectrum. It could have been anything, but to make it work, we're going to assume it's got some maximum frequency. It just happens to be kind of smooth in time, so it has no energy above omega sub m. Here is our P of t, our sampling sequence, or a set of impulses. And we said its Fourier transform is also a set of impulses at multiples of the omega sam, 2 pi on big T. When we multiply these in time, we convolve them in frequency, and when you convolve with something with a delta, you just get an image of the thing you're convolving centered around each delta. So here is the G sub P, the gated time domain function, and its spectrum, which is the original spectrum scaled by some scaling constant, depending on the height of these deltas, but then replicated at every one of these deltas. So we get this repetition of the original spectrum across all frequency. And we said that GP of t was equivalent to G of n. It's the same information. And we said that GP of j big omega was the same as G of eta j omega, just modulo a scale of the frequency axis. And so here's G of eta j omega, a function of little omega, which of course we know is periodic in 2 omega in 2 pi in little omega. And now that was sort of intrinsic to the way that we're defining it as the samples of on a unit circle in the z domain. So if the angle on the unit circle gets larger than 2 pi, we get the same value over again. But now we see, well, that works here because we've constructed a function of big omega, which is not constrained to be periodic. We've constructed one that is periodic with the right period, right? 2 pi corresponding to omega sam, and so that's why they can be the same overall frequencies. I'm not totally comfortable with the words that I'm using there. It's like it's sort of like where's the causality? What happened? it's not like we we sort of had to construct it this way and then magically it turned into this. But by building something that does have this identical functional form, identical form as the discrete time frequency, that's what happens when you multiply by this impulse train. Okay, but now we understand that multiplying by this impulse train is going to give us these images, these shifted versions of the spectrum in the continuous time domain, right? So this is our original signal is our baseband signal, and then when we sample it, when we multiply it, not sample it to turn into a sequence, just by sample it by multiplying it by this gating signal, which is basically the switch, the signal is going to the little sample and hold switch. We end up with a signal that has all these aliases, all these higher frequency copies of the original baseband signal. And now we sort of understand where we get the Nyquist limit, which is to say, well, we want the sampling rate to be at least double the highest frequency in the signal that we're sampling. Because if it isn't, if this sampling rate is less than twice this one, then these things are going to start to collide, and that's when we get aliasing distortion. Sampling is always going to give us a high frequency version, but as long as it falls into a region of a signal where there was no energy already, or no energy that we cared about, then we can ignore it. But if these aliases start overlapping, then we get distortion that we can't handle. So here's a case where we didn't sample high enough. We got some of this negative frequency alias spilling down below omega n. What happens when we actually build it is that, the frequencies in here, we can no longer tell whether they're energy coming from the baseband or from the alias image. We get some kind of mixture here, and so we've lost the information. We can't completely reconstruct. And so that gives us our simple version of the sampling theorem, that we have to sample at double the highest frequency. But what's interesting is that, of course, okay, and then here's what that actually means in practice. Experiments with band-pass filtered speech carried out in the 1920s found that you could understand speech pretty well if you low-passed it at around 3.4 kilohertz. Below 3.4 kilohertz, people's intelligibility started to fall. So when they were designing the telephone network, how much bandwidth they need to provide on the telephone network. That means that if we have 8 kilohertz sampling, then our Nyquist frequency is 4 kilohertz. We can preserve energy up to 4 kilohertz. That's the low-pass filter, the anti-aliasing filter we have to provide before in the A to D converter, and we're going to be fine. So 8 kilohertz sampling is the standard for normal telephony channels, digital telephony channels. But even though you can understand speech quite well, you can tell that it's not full quality speech. If you want transparent audio quality, then it's like, well, what is the frequency that if we low pass, you can't even tell there's a low pass filter in there? And that's somewhere towards 20 kilohertz. Depends how old you are. Young people have better high frequency hearing. As you get older, your bandwidth reduces. But at 20 kilohertz, there are very few people who can hear energy at that frequency. So for CDs, for digital audio, digital like music, we use a sampling rate of 44 kilohertz, which means the Nyquist rate is actually 22 kilohertz, but it means that you can build your aliasing filter that is down at minus 100 dB by 22 kilohertz, but still passes 20 kilohertz without any attenuation. So you've got a little bit of a transition band there. That's why it's a little bit more than 40 kilohertz. So that gives us our anti-aliasing filter. Now, here's the interesting twist of this understanding. Let's say we have a signal here which has got some fairly high frequency components in it, up here at omega h, but it's narrow band, so it only occupies this relatively small range of frequencies between omega L and omega h. Now, a simple application of the Nyquist theorem, sampling theorem, would say, well, we're going to have to sample at 2 times omega h in order to not have our aliases overlap with this, right? So if we sample at 2 times omega h, we get this entire image, we put it over here, and now this image of the negative frequencies doesn't overlap with our with our baseband image of the positive frequencies. But all that we care about is that these frequencies don't overlap with the image. If the image lands up falling somewhere down here, as long as there are no images that fall overlap with this, we could, in theory, still recover it. So with a signal like this, we could sample instead at this frequency here. And then we would end up with aliases here and here, coming from this. And then we'd also end up with aliases coming from here, from this sampling version here, which would be like here and here. But in this case, where the bandwidth just happened to be less than 1/4 of the total band that it was occupying, we can get away with a sampling frequency which is 1/4 of what the Nyquist theorem would otherwise dictate, because the aliases don't reconstruct. And then what happens is, we end up with this intrinsic signal. Basically, we'd normally look at the signal like this and then say, oh, and it repeats every 2 pi. Now, these frequency images are different from here, right? But when we do reconstruction, instead of putting a low-pass filter in here to pull out these parts, we can just put a band-pass filter here, pull out this image, and we've got the part that we want. The discrete time signal, which has all these aliased frequencies, it may be that the one you want to keep is not the lowest one, but some other higher frequency version. And so, the situations where you have a signal like this, which is in some frequency range but not in low frequency range, they're relatively rare. It comes up in communication, of course, quite a lot. But in communication, you're already aware of the fact that you're working in a strange part of the frequency spectrum. But it's just to make the point that, okay, there's a little bit more to this idea of sampling to avoid aliasing than just looking at your highest frequency and doubling it. Okay. That's all we've got time for right now. Any questions? All right, great. So I'll see you on Monday for the final project presentations.